Hi, and welcome to yet another video about vector stores. So, a short while ago, I made a lot of zero to rag videos, and I have previously made a what is rag video as well. This is much more deep level, and if you haven't seen any of those, definitely go see them. But I wanted to show what actually happens inside one of these vector stores from Community Toolkit and Microsoft Extensions Vector Data. And the best way to actually show what's inside is to try and build one yourself. So I did that. I did a very, very crude version. This is by no means something you can put into production. So I've only implemented exactly what we need. But let's go into it. So here under RAG, I have something called Build Your Own Vector Store. And what you can see here is we're using Azure OpenAI in order to do the embedding and talking to an agent. But we're not using any of the, let's go here, implementations of vector stores. There's a bunch of them, SQL, in-memory, Azure AI, and so on. And each one of them are dependent on the Microsoft Extensions vector data abstractions. And that extractions is the only one we put in here. So we have the baseline, but this by itself can't do anything. It's just contracts on how to build a vector store. Microsoft have built a lot. Let's build one ourselves. So before we do that, let's just quickly see the system, what's going on. So let's set a breakpoint and run it. So we have some data, just my handy internal null space data. And we built a client, and we built an embedding generator. Nothing new there so far. And then we built our vector store, but instead of the in-memory vector store, or the SQLite, or the SQL Server, and so on, we're building a My Vector Store. And we will go in and see how they are built behind the scenes. But for now, we just say we have a store. And just like we have a store, we can get a collection, and we can then delete that collection and make sure that it's there again. In real code, you would, of course, not delete the collection. Then we could embed the data. If I pull in this, you'll see that once I run in one, it's embedded one, and so on and so forward. So I would just let it run through all 10 here. And then I make a little search tool from this, the same from the previous video. I make a small agent that is allowed to ask a question, what is the Wi-Fi password, which was one of these up here. And when it answers, it will come back. Let's have a look that it could search. So this was my vector data store. And I built it from scratch because my vector store here is not something that exists other than in my files here. I have my vector store implementation here consisting of 3 files. And as mentioned in the beginning, this is the bare minimum of what we need. I have implemented get collection. I've implemented this, the upsert, and the search. There's a bunch of other methods here that I haven't taken into account. They would be possible to, of course, create, but that's not the point here. I wanted to show exactly this simple scenario, which is also the 95% of what you need. The rest could be done. It's just a lot of what's it called? Reflection. Yeah. So you will see a lot of reflection in this video. But let me run it again, and then let's go into exactly what happens in each one of these so you can get a better understanding what's going on. So let's run it. But instead of just moving over this, I will press F11 so we go in and see the implementation of this. So inside here, I have my vector store. And it takes in my vector store options. And as you can see, my vector store implements a vector store abstract class that made me needed to override a bunch of methods. And as you can see, some of them I've just left not implemented, but the get collection that we will use in 1 second is there. We will go into that in 1 second. The options are fairly simple. It's just an abstraction of a generic vector store collection. That means that we could add more options to a specific vector store, but in our case, we don't need to, so we don't do anything there. So that is the constructor here. Then when we say get collection, just like we have done with all the other collections, we go in and we actually just make a new collection. This collection can take in some definitions. This is the same thing you have inside the options with embedding generators and so on. So I've just said if we don't put in a definition, which we didn't, we just use the options we gave into the vector store by itself, so we can get our embedding generator into our collection. And if we go into the collection itself, you will see that this is again a class that inherits from an abstract class called vector store collection. And it has two generics, one for the key, in our case a string, and one for the record, in our case a vector model. So if we go out in here, you can see these are the two that we sent. So they're just normal generics, nothing special there. We have our system where we get in the name that we specified, and we get this definition, which I've now put in so we can have the embedding generator inside here as well. So I'm storing the name in the collection. I'm storing the embedding generator so we can do embeddings when we need to. And then I'm using reflection in order to get hold of what T-record is. So T-record is an object with 4 different properties. T-object is down here, if you haven't seen it before. So it's just a vector model, and we have some attributes. One that identifies the key, some that identifies additional values, and one that identifies the vector store vector itself. So when we have those 4, we can, of course, get the record key, because we need that in order to save it. This will be our primary key. And we need to get the vector record, which is just the one that was called vector. And then we, of course, have 2 additional properties. We can see here the question and the answer. So this is just reflection getting us that so we can work with it later on. And beyond that, the collection actually doesn't do anything. It's just an object in memory, and the only thing it's exposing is the name. The other ones we can only see because it's our own implementation. So we have our collection, and then it says ensure collection deleted. And I haven't talked about this yet, but my collection is actually just files. I've made a vector store collection in my temp folder, and inside that it will end up with some JSON files. Right now it's there because I've run it already, but when I say ensure collection deleted, it will go away, because what happens inside ensure deleted is I'm just gonna say I have a little folder helper to get my store, which is not a space, and it just takes the temp part, put in a vector collection, create that folder, and then it creates the store folder. My store folder is essentially just my temp folder / vector store collection. That's not a space. But this could be whatever you wanted. It could be a database that doesn't support systems, and you can build it behind the scene. I'm not saying this is easy to build, but it is possible to build. So I just made it using files. And then I'm just doing file manipulation in C# like normal. I delete the store using directory.delete, nothing to do with vectors or anything. And then I'm done. In the same way, when I create the collection, it's just give me the folder and create the folder here without anything in it. So that is just C#, and it's just our implementation details on how we want to do it. It could have been one big JSON file. It could have been binary files. It could be in blob storage. Probably not a good thing because that would give a lot of latency, but there's different options, of course. So now we have our collection. Not really done anything other than create a folder in a temp folder. But now we're going to go to each of our embeddings here. So when we do our embedding, we of course make our model. So again, we have the ID, question, answer, and the vector, which is built up of this. And we're just giving it an ID, and we are doing the upsert, meaning we either insert or update. So let's go in and see how that is implemented. And behind the scenes, there's actually two upserts. There's one for an individual record and one for multiple records. In our case, it's easier to just keep all implementation details in the multiple. So it's essentially just calling the other method. When I go in here, and again, get my store folder, because I need to put a JSON file here, because each vector record will become one JSON file in my implementation. Not efficient in any way, but it will work that way. So I go to my records, and then I use, again, reflection. I have my property key and my vector key, so I can get the value of the key, meaning just a grid in this case, and a vector value, which is the concatenation of question and answer, as we saw in this object here. So it's just the concatenation of that. And that is what I want to embed. So I'm using the embedding generator to generate one of these. We haven't really seen it because we just made the embedding generator and then magic happened behind the scenes. But this is what happens in real life, is that the embedding generator is being called for each record we put in, and we get an embedding. And that embedding is the 1536 dimensions, and behind the scenes it's just a bunch of floats here. Those we begin to put into a JSON object because we on the fly need to not save. We can't just serialize this object because that doesn't have a real vector. It has the representation of a vector. So we need to make our own object on the fly. In this case, I'm using JSON to do that. So I'm just building up a collection of the ID, which is our key, and the vector itself, which is the many floats in here. And then I'm taking the two additional records and also putting those into this direct dictionary. So we essentially have a dictionary of 4 things: ID, vector, question, answer, and that's it. And we just serialize that into JSON. So this JSON is very big with all the numbers here. And we're just writing that to the store. And we're using the key.json as our file name. When I do this, you see that we end up with one file. And if we look inside that file, it is what we saw in some of the other vector stores, something with an ID and a vector. And at the end, in this case, there's the question and the answer. We could have added more e-tags for a Cosmos DB and whatever we need in order to do things. Again, lots of crude implementation here, not even checking if the ID is something that makes sense in a database. But just to keep it simple, we go through that. We observe that way for all 10. And then come our search. So we put in our search tool here so we can see when the AI begin to use that search tool, how things will work. So we'll ask what is the Wi-Fi password against those 10 records we have in our vector store now, which is just 10 files. And here we go in and use the collection.search async. We search for what is the Wi-Fi password. In this case, the AI put a little extra in. And we want to have 3 of them back. So let's set a breakpoint here. I think I missed the breakpoint, so I'll just set one here and then we actually had it here. So we get our search input here, which is just a string. Technically, this could have already been a vector, but in our case, it's just a string. So we know that it's by the string value, we need to embed that. Because before we can search of just this text, we need to have it as an embedding, just like we have all the other ones as embeddings. So we actually make a new vector here. And this vector represents what is the Wi-Fi password. And it's just a lot of numbers as well. Then we go and grab all our files because we don't really have an easy way to figure out which of the ones are most similar. So we need to grab all records. That's inefficient, of course. If we had something that could search against an engine that could do similarity searches like a SQL Server can do, it will be more efficient. But since we just need all our files, we have our 10 JSON files. And for each of them, we go in and read the JSON. So we get the vector, the ID, and such, the long JSON file. We pass that JSON, and we generate a new T record, meaning we're trying to build up some of these, 10 of them. So we try to get our ID out. The ID is our GUID, and we put that into the record itself. Right now, the record is just using reflection, completely empty. But as soon we set this, we can see that the ID comes along. We can set the 2 other properties. So we get our question and we get our answer. So now we have that one property, but we had also the vector. So we can grab the vector element, and that's just the floating values of a lot of things here. We need to have that as a read-only float because that's how vectors normally are represented here. Looks the same as the float here. And then we need to take that individual vector, actually find out how close is it to the search vector. So we are going to make a score from the vector to the search embeddings vector. And this code is something I just had an AI agent match up. I'm not a mad expert, but it's a co-similarity search here that simply goes in and take vector A, vector B, and do a bunch of math related stuff, figuring out which one of them are closest to each other. And I have no clue how that actually works, but it will give a value between 1 and 0 and 1. And the higher the value, the more similar it is. For other vector stores, they might do other implementations. This is probably very, very crude and very, very slow compared to what others can do, but it's just math behind the scenes doing vector similarity searches. And we find in this case that this was 0.1, meaning 10% similar. So we take that score, put it out, and we put it into this vector search result, which is a common object of what we get back. Here, let me find it in the search, what we get back here. So we make one of those. So we essentially have that now this record, who's in charge of the report, this answer, and this ID has this score. And then we do that for every single file, meaning all 10. So if I set a breakpoint here and let it run, get rid of that one, we now have all 10 records. And for each one of them, we have the record itself and the score. Some of them are high, some of them are low. And then I just sort them by the highest score and take top, in my case, 3. So we can get that back, and we need to give it back as an async enumerable. So we need to do it in yield return here. So essentially what's happening is it will run that, and let me set the breakpoint in here so we can see that the first results come back, the one with the highest score, and luckily for us, that highest score is what is the Wi-Fi password at the office. And by then, once we have all 3 out that we wanted, we get our search result back, which will look like this, that we can then augment onto the call using this, in this case, the tool, and we can run to completion, where it will actually have done it using files on my machine, where each one of them have a long vector, an ID, and a QA. And that's actually everything there is to what's happening behind the scenes. Again, this is very, very crude, but the crude part is that I'm doing a reflection here without any error handling or any sense of optimization and speed and stuff. If you want to have a look, the community toolkits implementations are open source, so you can go in and check. There's a bunch of extra things. There's something called a model builder and all kinds of things, but I wanted to keep it very, very simple here with code that is easy to see and understand. So we, in 150 lines of code, have a vector store that can do the most basic things of what we need. Of course, we would need to implement get async of a specific ID, but it will essentially, if we keep it the same way like this, just be more reflection here, and so on. But that's everything there is to how to actually look what happens inside a vector store. I have some ideas of actually building one at one point, but that will be for another video. So if that ever happens, then see you there. Bye for now.